Hello and welcome to the first day of Unit 5. Today we start looking at integration. Now, we are going to jump right into things in this unit. I want to talk briefly about some notation and some vocabulary, but we're going to move fairly quickly into this, sort of dive right in, and then we'll slow down and look at integration more deeply once we get further into the unit. Now, the integral, okay, is an operator, sort of like the derivative, but it's the reverse. Okay, so a lot of times we call integration anti-differentiation, or the integral of f gives you the antiderivative of f, okay, where the derivative of this function is f. So we have the integral sign, okay, and the integral sign could have bounds on it, like a, b, 0 to 3, u to v, 0 to t, okay? And those bounds of integration are called just that, bounds of integration. And when I have bounds of integration, then I can find what's called the definite integral, okay? Today we're going to be looking at indefinite integrals, and those are integrals that don't have bounds. We're really just going to be looking at anti-differentiation, so doing the derivative of things in reverse. Okay, this thing is called the integrand. Okay. This is your differential, and that tells you what you're integrating with respect to, which is important, because if that's not there, then you can't take the integral, because you don't know what to take the integral with respect to. Okay. This is my antiderivative. All right, and C, very important, is my constant of integration. Anytime I take the integral of something and it's not a definite integral, I get a constant of integration. Okay. So these are the vocabulary, the parts of the integral, the things that we're going to be dealing with today. As we're introduced to other aspects of integration, we'll go over that when we get to it. But this is what we need to know for today. Okay. I guess it would be good to see that. Okay, so if capital F is the antiderivative of f, then it must be true that the derivative of f is that, and that's how we're going to check our work to make sure that we've done things correctly. All right, so let's take a look at a few examples. Okay, so remember what I said. When I'm doing the integral of something, so in this case, this is the integral of 10x to the fourth minus 2 secant squared x dx, The differential tells me what I'm taking the integral with respect to. So what variable I'm taking the integral with respect to. In this case, it's x. This is an indefinite integral because I don't have bounds. And remember, the answer that I get is the antiderivative of this function. Okay? In other words, the answer that I get, I should be able to take the derivative of it and get what's in here. So what we're going to do for the first piece is the power rule in reverse. So instead of multiplying by the current exponent and decreasing it by 1, we're going to increase the current exponent by 1 and then divide by the new exponent. So we get 10x to the 5th over 5 minus. Okay, now the derivative of what is secant squared? Well, it's tangent. Okay, and don't forget, every time you find an indefinite integral, you always get a constant of integration. That's very important. Okay, that constant of integration exists every time you find an indefinite integral. Now, obviously that can reduce to 2, and we can check our work by finding the derivative of this. Okay, so let's check our work in green here. Okay, 5 times 2 is 10. X decrease the power by 1 minus 2. The derivative of tangent is secant squared. And the derivative of a constant is 0. So that constant of integration disappears. And I get back my integrand. So pretty straightforward. Okay, so going forward, if you're having trouble now with your differentiation rules, the rest of the year is going to be very difficult. Okay, so you really do need to know those differentiation rules. Okay, all of those formulas, because when we get to doing anti-differentiation, I mean, knowing those derivative rules is the same as knowing the integral rules, just in reverse. So you really do need to have those down. All right, so let's start here. This is example 2, and this is example 3, I believe, in your notes. Okay, now this guy is interesting. I can't quite integrate this just yet. Okay? I can't do the power rule with the outside and then the inside. I can't do that. So the easiest thing for me to do would be to just go ahead and expand this. Okay, and rewrite this as the integral of 4 plus 4x squared plus x to the 4th. Okay, and now the integral becomes much simpler to compute. We get 4x plus 4/3 x cubed plus 1/5 x to the 5. Don't forget your constant of integration. Okay. Moving on. This guy, again, a rational function, something that we don't really want to have to deal with. So let's get rid of the denominator here and break this up into a new integral that is 3x to the 3rd minus 2 plus 5 over x dx. Okay. And then we can just integrate this term by term. Okay, so the integral here, oops, that's a 4. Oh, no, it's not. I forgot because I canceled one of the factors of x there. Okay, so we get a 3/4 x to the 4 minus 2x plus the derivative of what gives me 1 over x? Natural log of x. So we get 5 times the natural log of x. Don't forget the constant of integration. Okay. Now remember, you can always go back and check these simply by taking the derivative. And we could do that in our head, right? The derivative of 4x is 4. The derivative of 4/3 x cubed is 4x squared. The derivative of 1/5 x to the 5 is 1 times x to the 4th. And the derivative of a constant is 0, so it disappears. Okay. And you can do the same thing here, checking your work by taking the derivative of the antiderivative and seeing if you get the integrand. Okay. All right, so now what we're going to look at is what's called an initial value problem. Okay. I'm starting with a differential equation. It's an equation that has differentials in it. That's all it is. All right. And what I'm going to do here is I'm going to separate my differentials dy and dx by multiplying both sides. Oops. And actually, I'm going to go ahead and rewrite this as x to the 1/3. Okay. Now, by integrating both sides of the equation, okay, the integral of 1 with respect to y is just y. Okay? And the integral of x to the 1/3 is x to the 4/3 times 3 over 4 plus c. Now, I have this initial value that I can use to solve for c. Okay. So when I plug in 1, I get 2. So what did c have to be? Well, c had to be 5/4, right? Yeah. Okay. So I can solve this initial value problem and say that the original function was y equals 3 over 4 x to the 4/3 plus 5/4. Okay. So I get the full function, the initial function, and it's all based on that initial condition. Okay. Let's try another one. And we're going to multiply again both sides by dx here. We'll end up with dy equals sine x plus 1 dx. And by integrating both sides, I get a y equals the integral of sine is negative cosine. Because remember, what's the derivative of cosine? It's negative sine, and the two negatives cancel out and give me a positive sign. Okay? And then the integral of 1 with respect to x is x. All right. Now keep in mind that this x is the only thing that's in the argument of cosine. Okay, not the other x. All right. And then I do get a plus c. Now, my initial condition is that at pi over 3, I'm at a half. All right, well, let's see. Negative cosine of pi over 3. Pi over 3 is like 60 degrees, and cosine would be about a half. So that's negative a half. half plus a half is 1. So it looks like C's got to be 1 minus pi over 3 or 1 minus pi all over 3. Okay, so my final answer here is the equation y equals negative cosine x plus 1 minus pi over 3. That's the value for C that I got with this initial condition. Okay. So again, these are called initial value problems because they're it's some differential equation. I've given an initial value so I can do an integral, and then solve for my constant of integration by plugging in the initial value and solving for C. Okay. And then my answer is the function of y.